Welcome to The Explainer. Today, we're tackling a huge one, the story of how we discovered our universe isn't just expanding, it's speeding up. It's a real cosmic detective story with clues, a shocking plot twist, and a mystery that's still unfolding today. So let's rewind to the 1990s. The biggest question on every cosmologist's mind was pretty simple. What's the ultimate fate of our universe? Was it going to expand forever and just fizzle out? Or was gravity going to win in the end and pull everything back together in a big crunch? At the time, pretty much everyone thought they knew the answer. I mean, it just makes sense, right? The universe is packed with stuff. Galaxies, stars, gas, and all that stuff has gravity. So just like when you throw a rock in the air and Earth's gravity slows it down and pulls it back, the combined gravity of the entire universe should be acting like a giant brake on the expansion from the Big Bang. It had to be slowing down.
Okay, so here's the crucial point. The scientists who set out on this mission weren't looking for some crazy new exotic discovery. Not at all. They were just trying to measure something they were absolutely sure was happening, how much the universe was slowing down.
Think about it. If you could measure the precise rate of that slowdown, you could essentially put the whole universe on a scale. That single number would tell you if there was enough stuff, enough gravity, to one day stop the expansion and reverse it, or if we were just going to expand forever. The fate of everything hinged on this one measurement. So, to measure this cosmic slowdown, our detectives needed a really special tool. They needed a kind of cosmic yardstick that could measure unimaginable distances across space and, by doing that, look back in time. And they found the perfect tool in these incredible stellar explosions called Type I supernovae. Now, these aren't just any old exploding stars. What makes them special is that they are all remarkably, consistently bright, which makes them the perfect standard candle for this job. It's kind of like seeing car headlights on a pitch-black road. You have a pretty good idea of how bright headlights are supposed to be, right? So you can tell in an instant if a car is close or miles away just based on how dim the lights appear. Type A supernova work the exact same way. We know how bright they are supposed to be, so how dim they look tells us exactly how far away they are. So why are they so consistent? Well, it all comes down to the physics. It starts when a super-dense star starts siphoning off material from a nearby companion star. Once it hits this very precise weight limit, about 1.4 times the mass of our sun, it becomes unstable, and boom, it triggers a massive thermonuclear explosion. Because the trigger is always the same, the explosion is always the same brightness. A perfect standard candle.
There was just one little problem. A big one, actually. An explosion like this only happens in a galaxy our size about once every 100 years. So, just picking a galaxy and waiting around wasn't really a great option.
So astronomers had to get clever. They basically had to play the cosmic lottery. Using amazing new wide-field cameras, they could take a snapshot of tens of thousands of galaxies all at once. Then, they'd come back a few weeks later, take another picture of the same spot, and digitally subtract the first image from the second. Everything that stayed the same would just disappear, leaving behind only the things that had changed, like a brand new distant supernova. All right, so the stage is set. The teams have their standard candles, they have their method for finding them, they pointed their telescopes to the farthest reaches of space, gathered all the data, and got ready to calculate exactly how much the universe was slowing down. But that's not what they found. Not even close.
The results were, well, they were baffling. If the universe's expansion was slowing down like everyone thought, then the most distant supernova should have been closer to us, and they should have appeared brighter than predicted. But the data showed the complete opposite. The supernova were dimmer, and that could only mean one thing. They were much, much farther away than any of our models could explain.
This was completely backwards. The universe wasn't slowing down at all. It was speeding up. Something was out there pushing galaxies apart, acting like a kind of anti-gravity, and it was overpowering the pull of all the matter in the entire cosmos. So when you get a result this revolutionary, you have to find an explanation. The teams checked and rechecked everything. There was no mistake. Some unknown force had to be responsible for this cosmic acceleration. A new culprit had to be found. The prime suspect was actually an old idea, something Albert Einstein had come up with and then famously called his biggest blunder. It was the idea that empty space itself has its own built-in energy, a kind of negative pressure that constantly pushes outward. They needed a name for this mysterious force, so they called it dark energy. And here's where the scale of this discovery really hits you. This mysterious dark energy wasn't just some minor thing happening out at the edges. No. It turns out it makes up almost 70% of the entire universe. All the normal matter, the stuff that makes up you, me, and every star we see, that's only about 5%. We were living in a universe totally dominated by something we never even knew existed. What's pretty amazing is how quickly the idea was accepted. And that's because, as strange as it sounds, dark energy was like a magic puzzle piece. It suddenly solved a whole bunch of other nagging problems in cosmology. All at once, the age of the universe made sense. The 70% of missing energy was found. It all just clicked. It was the crazy idea that just happened to work perfectly. So the discovery of dark energy closed one case file, but it immediately opened up a brand new one with even deeper questions. And today, those questions have led us to another major crisis in our understanding of the cosmos. It's called the Hubble tension. And basically, it means we have two of our very best, most reliable ways to measure how fast the universe is expanding right now, and they give us two different answers. And this isn't some small rounding error. It's a fundamental conflict right at the heart of modern cosmology. Okay, so here's the breakdown. On one side, we can look at the afterglow from the Big Bang, the early universe, and use our best model of physics to predict how fast the universe should be expanding today. That gives us a number around 67. Then, on the other side, we use those same trusty Type Y supernova to directly measure the expansion of the local universe around us right now, and that gives us a higher number, around 73. Now, the problem is, as our telescopes and our methods get more and more precise, these two numbers aren't getting closer together. They're actually drifting farther apart. The error bars don't overlap anymore. This is a huge hint that our standard model of cosmology, the fundamental story we tell about the universe, is missing a key ingredient. There's a chapter we haven't read yet. But ultimately, attention like this isn't a failure. It's a clue. It's the universe basically telling us that our understanding is incomplete. Just like those dim supernovae pointed the way to dark energy 2 decades ago, this disagreement could be pointing the way to the next revolution in physics. The question now is, what incredible new discovery is waiting for us just beyond the edge of what we think we know?